Space is filled with familiar worlds, giant planets, frozen moons, and endless fields of rock, drifting quietly through the darkness. But sometimes, a small and seemingly unimportant world hides something that no one expected. Between Mars and Jupiter lies a region crowded with ancient debris, the asteroid belt. For centuries, astronomers believed this region contained nothing more than leftover fragments from the early solar system, broken rocks, silent relics. Yet one object there is different, larger than the rest, round like a miniature planet, a world that quietly holds its own gravity together in the middle of this cosmic rubble. Its name is Ceres. At first glance, Ceres looks like a dark, ordinary dwarf planet, cold, cratered, and ancient. The kind of place you might expect to be completely lifeless and uneventful. But when spacecraft finally arrived and began mapping its surface, scientists noticed something strange. Scattered across the grey landscape were bright, glowing spots, patches so reflective they looked almost like lights shining from the darkness of space. For a moment, no one knew what they were. Salt, ice, something erupting from beneath the surface. The mystery became one of the strangest discoveries in the asteroid belt, because Ceres, the largest object between Mars and Jupiter, may not be as dead as it once appeared. We're traveling to this quiet dwarf planet to explore one of the solar system's most unexpected mysteries. If you enjoy calm journeys through space and the strange worlds hidden within it, consider subscribing, and let's begin our exploration of Ceres, the dwarf planet with the mysterious bright spots. Far beyond the familiar worlds of Earth, Mars, and Jupiter, there exists a quiet region of space that most people rarely think about. It lies between the rocky inner planets and the massive gas giants, a vast band of scattered debris orbiting the sun in slow, silent motion. This region is known as the asteroid belt. For centuries, astronomers believed it was nothing more than a chaotic graveyard of broken rocks, fragments left over from the birth of the solar system more than 4.5 billion years ago. To early observers, the asteroid belt seemed unremarkable. Through telescopes, these objects appeared as faint points of light, too small and distant to reveal much about their nature. They were catalogued, named, and measured, but few people imagined that one of these worlds might be hiding something extraordinary. Among those countless drifting bodies, however, there is one object that stands apart. It is larger than most asteroids, rounder, more complex, a world that, despite its relatively small size, behaves more like a planet than a simple rock. That world is called Ceres. Ceres is the largest object in the asteroid belt, and the only one classified as a dwarf planet in this region of space. With a diameter of about 940 kilometers, it is far smaller than Earth, but it still dominates its neighborhood. In fact, Ceres contains nearly a third of the entire mass of the asteroid belt combined. When astronomers first discovered Ceres in 1801, it caused enormous excitement. For a brief time, scientists even believed they had found a new planet. Its orbit fit perfectly between Mars and Jupiter, a location where some astronomers had long suspected another planet might exist. But as telescopes improved and more objects were discovered in the same region, it became clear that Ceres was not alone. It was simply the largest member of a vast family of asteroids. For many years after its discovery, Ceres remained a mystery. Because it was so small and so far away, even powerful telescopes could reveal only the faintest hints of its surface. From Earth, Ceres looked like nothing more than a tiny grey sphere. Its secrets remained hidden in the darkness of deep space. Yet scientists suspected that Ceres might be different from the typical asteroids surrounding it. Most asteroids are irregular chunks of rock, shaped like jagged potatoes, drifting through space. But Ceres is different. Its gravity is strong enough to pull its material into a roughly spherical shape. This makes it more like a miniature planet, a world with its own geological history. For decades, researchers wondered what the surface of this distant dwarf planet might look like. Was it a frozen, lifeless rock, like many other asteroids? Or did it have a more complex story to tell? These questions remained unanswered until the early 21st century, when humanity finally sent a spacecraft to investigate this strange world up close. The mission responsible for this journey was NASA's Dawn spacecraft, launched in 2007. Dawn was designed to explore two of the largest bodies in the asteroid belt, Vesta and Ceres. The spacecraft used an advanced propulsion system known as ion engines, allowing it to slowly spiral through space for years at a time. After studying the giant asteroid Vesta, Dawn set course for Ceres, traveling hundreds of millions of kilometers across the solar system. In March of 2015, after nearly 8 years of travel, Dawn finally arrived at its destination. For the first time in history, a spacecraft entered orbit around a dwarf planet in the asteroid belt. As Dawn approached Ceres, scientists eagerly waited for the first clear images of the surface. Until that moment, Ceres had remained little more than a blurred disk in telescope photographs. No one knew exactly what they would find. At first, the images revealed what many researchers expected. The surface appeared grey and heavily cratered, similar to many other rocky worlds in the solar system. Ancient impact scars marked the terrain, evidence of billions of years of collisions with wandering asteroids. But then something unusual appeared in the photographs. Within one of the craters, scientists noticed a strange feature, a bright reflective patch that stood out dramatically against the dark landscape surrounding it. At first, it looked almost like a light shining from the surface. As Dawn moved closer, the feature became even clearer. In fact, there were not just one, but several bright spots clustered together inside a large crater known as Occator Crater. The brightness of these spots was astonishing. Compared to the surrounding terrain, they reflected far more sunlight, making them appear almost luminous when seen from space. This discovery immediately captured the attention of scientists around the world. Bright features like these are extremely unusual on dark, rocky worlds. Most asteroids and dwarf planets have surfaces covered in dark, dusty material that absorbs sunlight rather than reflecting it. Yet here on Ceres, something different was happening. The bright spots were so reflective that they almost looked like patches of snow or ice. At first, scientists wondered whether these areas might indeed be made of exposed water ice. If true, it would suggest that Ceres still contained frozen water near its surface, an exciting possibility for researchers studying the history of water in the solar system. But as Dawn collected more detailed images, the mystery deepened. The bright spots were not smooth sheets of ice. Instead, they appeared as rough, fractured deposits scattered across the floor of the crater. Some of them formed intricate patterns, almost like mineral crystals shining in the sunlight. Spectral analysis eventually revealed that these bright deposits were composed primarily of sodium carbonate, a type of salt. This discovery raised an even more intriguing question. Salt deposits like these typically form when liquid water evaporates, leaving behind mineral residues. On Earth, such formations are common in dried lake beds and ancient oceans. But Ceres is a small, cold world, located hundreds of millions of kilometers from the sun. Where could liquid water possibly come from in such an environment? To answer this question, scientists began examining the structure of Ceres more closely. Evidence suggested that beneath its rocky surface, Ceres might contain a large amount of water ice. In fact, some models indicate that up to a quarter of Ceres' total mass could be composed of frozen water. If this is true, Ceres may actually be more like an icy moon than a typical asteroid. Even more fascinating is the possibility that deep beneath the surface, pockets of briny liquid water might still exist today. These underground reservoirs could slowly seep upward through cracks in the crust. As the salty water reaches the surface and evaporates in the vacuum of space, it would leave behind bright mineral deposits exactly like the ones seen inside Occator Crater. If this process is still happening, it means that Ceres may not be a completely dead world. Instead, it could be geologically active even today. This idea was once considered almost impossible for such a small object. Normally, small bodies cool and solidify quickly after they form, leaving them geologically inactive for billions of years. But Ceres appears to challenge that assumption. Additional evidence came from another surprising feature discovered on its surface: a strange mountain known as Ahona Mons. Unlike the surrounding cratered terrain, Ahona Mons rises sharply above the plains like a solitary pyramid. It stands about 4 kilometers tall, with steep slopes and a smooth appearance that looks very different from typical impact craters. Scientists now believe that Ahona Mons may be a cryovolcano. Cryovolcanoes are similar to regular volcanoes, but instead of erupting molten rock, they release icy materials such as water, ammonia, or salty slush. In other words, parts of Ceres' interior may once have been warm enough for liquid materials to move and erupt onto the surface. If this interpretation is correct, then Ceres is not just a frozen asteroid. It is a complex world with a dynamic past and perhaps even a slowly evolving present. All of this raises an intriguing possibility. Could Ceres once have contained conditions suitable for life? While it is unlikely that life exists there today, the presence of water, salts, and internal heat suggests that long ago the interior of Ceres might have been far more active than it is now. In the early days of the solar system, when heat from radioactive elements and frequent impacts warmed the interiors of small worlds, Ceres may have possessed a deep subsurface ocean hidden beneath its crust. If so, it would join a growing list of ocean worlds scattered throughout the solar system. Places like Europa, Enceladus, and Titan, where hidden water reservoirs may still exist beneath icy shells. For a world that was once dismissed as just another asteroid, Ceres has turned out to be far more fascinating than anyone expected. And yet, despite everything scientists have learned from the Dawn mission, many mysteries remain. The bright spots continue to puzzle researchers. The internal structure of the dwarf planet is still not fully understood, and the possibility of hidden liquid reservoirs beneath the surface continues to spark curiosity among planetary scientists. Ceres, it seems, is a world that still has many stories left to tell. A quiet dwarf planet drifting in the asteroid belt, yet holding clues about water, geology, and the early history of our solar system. And as we continue exploring these distant worlds, discoveries like this remind us of something important. Sometimes the smallest planets can hide the biggest surprises. Long before spacecraft ever reached Ceres, scientists had already begun to suspect that this small world might be very different from the other asteroids surrounding it. The clue came not from photographs or close-up observations, but from something much more subtle: its shape and gravity. Most asteroids in the solar system look like broken rocks. Their shapes are irregular, jagged, and uneven because they simply do not have enough gravity to pull themselves into spheres. When these bodies formed billions of years ago, they remained frozen in whatever shapes they originally took. But Ceres is different. Even through early telescopes, astronomers noticed that Ceres appeared slightly round. Later measurements confirmed this. The dwarf planet is nearly spherical, meaning its own gravity has pulled its material inward over time, smoothing its shape into something closer to a miniature planet. This alone was enough to set Ceres apart from the countless other objects in the asteroid belt. But the implications went much deeper. A spherical shape usually means that an object once had enough internal heat to allow its materials to shift and reorganize. In other words, at some point in its history, the interior of Ceres must have been warm enough for its rock and ice to slowly flow under gravity. That realization led scientists to an important question. If Ceres once had internal heat, what happened inside this small world during its early formation? To answer that, we have to travel back in time to the chaotic birth of the solar system more than 4.5 billion years ago. Our solar system was not the calm place we see today. Instead, it was a swirling disk of gas, dust, and debris orbiting a young sun. Within this disk, tiny grains of material slowly collided and stuck together, forming larger and larger clumps. Over millions of years, these clumps grew into kilometer-sized bodies known as planetesimals. Some of these planetesimals eventually merged to form the planets we know today. Others remained smaller, becoming asteroids, dwarf planets, and icy moons. Ceres was one of these early planetesimals, but unlike many of its neighbors, it managed to grow relatively large. Its size gave it an important advantage. During the early stages of the solar system, newly formed objects often contained short-lived radioactive elements such as aluminum-26. As these elements decayed, they released heat inside the bodies that contained them. For larger objects like Ceres, this internal heating may have been strong enough to partially melt the ice within its interior. If that happened, Ceres may have briefly possessed something extraordinary, a subsurface ocean. Deep beneath its rocky crust, liquid water mixed with salts and minerals could have formed a global layer surrounding its interior. For a world less than 1,000 kilometers wide, this would have been remarkable. Many scientists believe that during its earliest history, Ceres was not simply a frozen rock drifting through space, but a much more dynamic world, one where liquid water slowly circulated beneath the surface. Over time, however, things changed. Because Ceres is relatively small, it could not retain heat for billions of years like larger planets can. As the radioactive elements decayed and the interior gradually cooled, any liquid water that once existed likely began to freeze. The subsurface ocean may have slowly solidified into layers of ice mixed with rock and salts. Yet evidence suggests that this freezing process may not have been completely uniform. Instead of forming one solid block, parts of the interior may have remained partially liquid for far longer than expected. This idea became especially interesting after the arrival of the Dawn spacecraft. When Dawn began mapping the surface of Ceres, scientists noticed something curious about its craters. Normally on small rocky worlds like the Moon or Mercury, impact craters remain sharp and well-defined for billions of years. Their edges stay steep and their shapes remain clearly visible. But many craters on Ceres appear softened and partially flattened, as if the surface material slowly relaxed after the impacts occurred. This kind of behavior is more typical of icy worlds, where the surface can slowly flow and deform over long periods of time. It suggested that the crust of Ceres might not be made entirely of solid rock. Instead, it could be a mixture of rock and ice, something softer, capable of gradually reshaping itself under its own weight. Another surprising discovery supported this idea. When Dawn measured the gravitational field of Ceres, scientists found evidence that the dwarf planet's interior may be partially differentiated. Differentiation is a process that happens when materials inside a planetary body separate according to their density. Heavier materials sink toward the center while lighter materials rise toward the surface. On Earth, for example, heavy iron sank to form the planet's core, while lighter rock formed the mantle and crust. Ceres appears to have experienced a simpler version of this process. Its interior may consist of a rocky core surrounded by layers rich in ice and salts. This structure would make Ceres something like a hybrid between an asteroid and an icy moon. And if some heat still remains trapped inside this layered interior, it could explain some of the strange geological features seen on the surface. One of the most fascinating examples is Occator Crater, the location of the mysterious bright spots discovered by the Dawn spacecraft. Occator is about 90 kilometers wide, making it one of the largest and most dramatic impact structures on Ceres. At the center of this crater lies a region known as Ceres faculae, the brightest area on the entire dwarf planet. When sunlight hits this region, it reflects so strongly that it appears almost glowing compared to the surrounding terrain. At first, scientists were puzzled by how these deposits formed, but as Dawn collected more data, the pieces of the puzzle began to fall into place. The bright spots are made primarily of sodium carbonate, a salt commonly associated with evaporated water. This suggests that at some point in the past, salty liquid from beneath the surface must have reached the crater floor. One possible explanation involves the impact that created Occator itself. When the asteroid struck Ceres and formed the crater, the immense energy of the collision may have fractured the crust deeply enough to open pathways into the interior. Through these fractures, briny liquid from below could slowly seep upward. When this salty water reached the surface, it would quickly evaporate in the vacuum of space, leaving behind bright mineral deposits. Over time, repeated flows of this brine could have built up the reflective patches we see today. Even more intriguing is the possibility that this process may still be happening. Some measurements from Dawn detected faint hints of water vapor in the region, suggesting that small amounts of gas might still occasionally escape from the surface. If true, this would mean that Ceres remains geologically active even billions of years after its formation. Such activity is rare for a body of this size. Most objects smaller than planets lose their internal heat quickly and become completely inactive, but Ceres may still hold enough residual heat to allow slow movement of briny liquids within its interior. This raises an important question about the nature of dwarf planets themselves. For a long time, scientists assumed that small worlds were simple and inactive, little more than frozen leftovers from the solar system's formation. But discoveries over the past few decades have begun to change that view. We now know that even relatively small bodies can be surprisingly complex. Pluto has glaciers made of nitrogen ice. Enceladus, a tiny moon of Saturn, shoots enormous plumes of water into space. Europa hides a global ocean beneath its icy shell. And now Ceres, quietly orbiting in the asteroid belt, shows signs of having once contained liquid water and possibly even ongoing geological activity. Each new discovery reminds us that the solar system is far more diverse than we once imagined. And perhaps most fascinating of all is the realization that worlds like Ceres may preserve clues about the earliest history of our planetary system. Because Ceres formed very early, it may still contain ancient materials that have remained largely unchanged for billions of years. Studying this dwarf planet is therefore like opening a time capsule from the era when the planets themselves were just beginning to form. Inside that time capsule may lie answers to questions scientists have been asking for generations. How did water spread throughout the solar system? What processes shaped the earliest planetary bodies? And how common might hidden oceans be on small worlds scattered across the cosmos? Ceres may not look dramatic at first glance. It is a quiet grey sphere drifting silently between Mars and Jupiter, but beneath its ancient surface lies a history that is far more complicated than anyone once believed. A history shaped by water, ice, impacts, and slow geological change. And as researchers continue studying the data returned by the Dawn mission, they are slowly uncovering the story of a dwarf planet that turned out to be anything but ordinary. For most of human history, the asteroid belt was imagined as a chaotic and dangerous place, a dense swarm of rocks constantly colliding with one another as they raced around the sun. Early science fiction stories even described it as a deadly obstacle course that spacecraft would struggle to navigate. But the reality is very different. In truth, the asteroid belt is mostly empty space. Although it contains millions of rocky bodies, the distances between them are enormous. A spacecraft traveling through this region is far more likely to encounter nothing at all than to pass near another asteroid. And yet, among this quiet collection of ancient debris, Ceres stands as something truly unique. It is not just the largest object in the asteroid belt, it is also the most planet-like body in the entire region. To understand why, scientists began studying its gravity, composition, and internal structure in greater detail. Once the Dawn spacecraft entered orbit, one of the most important discoveries came from measurements of the dwarf planet's density. Ceres has an average density of about 2.16 grams per cubic centimeter, which is significantly lower than the density of solid rock. This number immediately told researchers something interesting. It meant that a large portion of Ceres must be composed of ice or other lighter materials rather than dense rock alone. In fact, scientists now estimate that as much as 25 to 30% of Ceres' mass may be water. That is an astonishing amount. If all the water contained within Ceres were melted, it could form a global ocean covering the dwarf planet with a layer tens of kilometers deep. To put that into perspective, Ceres may contain more fresh water than Earth's surface oceans, even though the dwarf planet itself is far smaller than our world. This discovery transformed the way scientists thought about Ceres. Instead of viewing it as a simple asteroid, researchers began to see it as a water-rich world, a body that formed in a region of the solar system where ice was abundant. But this raised another important question. If Ceres contains so much water, why isn't its surface covered in ice? After all, many icy moons in the outer solar system have bright reflective surfaces made of frozen water, but Ceres appears dark and grey when viewed from space. The answer likely lies in the composition of its crust. The surface of Ceres is covered by a mixture of rock, clay-like minerals, and dark carbon-rich compounds. These materials create a dusty layer that hides much of the ice beneath. Over billions of years, constant impacts from smaller asteroids may have gradually mixed the surface material, creating a thick crust of dark debris. This crust acts like an insulating blanket. It traps ice below the surface, protecting it from sublimating, the process where ice turns directly into vapor in the vacuum of space. However, the crust is not perfectly sealed. In certain places, cracks and fractures allow subsurface materials to reach the surface. When this happens, water ice or salty brines may briefly appear before evaporating away. This process likely explains some of the unusual features seen on Ceres today. One of the most intriguing of these features is the presence of organic molecules on the dwarf planet's surface. Organic molecules are carbon-based compounds that are often associated with the chemistry of life. They do not necessarily indicate that life exists, but they are important ingredients in biological processes. In 2017, scientists analyzing data from the Dawn spacecraft detected regions on Ceres that contain unusually high concentrations of organic materials. These compounds were found near a large crater called Occator Crater. The discovery immediately sparked excitement among researchers. Organic molecules can form in several ways. Some are created through chemical reactions in space, while others may originate inside planetary bodies through interactions between water, minerals, and heat. Either possibility is fascinating. If the organic compounds on Ceres formed locally, it would suggest that the dwarf planet once had environments where complex chemistry could occur, possibly involving liquid water. On the other hand, if the organics arrived from outside sources, such as impacts from comets or carbon-rich asteroids, it would provide insight into how organic materials spread throughout the early solar system. Either way, Ceres appears to contain a surprising combination of water, salts, and organic compounds, three ingredients that are often associated with environments capable of supporting life. Of course, Ceres itself is extremely cold today. Surface temperatures average around -105 degrees Celsius, far too cold for liquid water to exist on the surface for long. But deep below the crust, conditions may once have been very different. Scientists now believe that the interior of Ceres may have experienced long periods of slow chemical evolution as water interacted with rock inside the dwarf planet. It could have produced clay minerals and other hydrated compounds. These materials have indeed been detected across much of the surface. The presence of these minerals suggests that Ceres once contained large amounts of liquid water circulating through its interior. Over time, as the dwarf planet cooled, that water likely froze into thick layers of ice mixed with salts and rock. But freezing water does something interesting. When salty water begins to freeze, the ice that forms tends to exclude the dissolved salt. As a result, the remaining liquid becomes increasingly concentrated with minerals. This process can create dense pockets of extremely salty liquid known as brines. Brines have a lower freezing point than pure water, meaning they can remain liquid even at very cold temperatures. Inside Ceres, these briny reservoirs may have persisted for far longer than scientists once believed possible. Occasionally, these liquids may still find their way to the surface through fractures created by impacts or internal stress. When they reach the surface, they quickly freeze or evaporate, leaving behind bright mineral deposits like the ones seen in Occator Crater. This slow, quiet geological activity paints a very different picture of Ceres than scientists imagined in the past. Instead of being a completely dead world, Ceres may still be slowly evolving. Its interior may contain pockets of briny liquids trapped beneath layers of rock and ice. Over millions of years, these liquids could occasionally rise toward the surface, reshaping parts of the dwarf planet in subtle ways. Another clue supporting this idea comes from the overall shape of the craters on Ceres. Many craters appear shallower than expected, suggesting that the surface material may gradually relax over time. This process, known as viscous relaxation, occurs when icy or soft materials slowly flow under the influence of gravity. It is commonly observed on icy moons like Ganymede and Callisto. Seeing similar effects on Ceres suggests that its crust contains significant amounts of ice mixed with rock. In other words, the dwarf planet's surface is not entirely rigid. Given enough time, its landscape can slowly reshape itself. All of this evidence points to a fascinating conclusion. Ceres may represent a transitional type of world, something between a rocky asteroid and an icy moon. It formed in the asteroid belt, but it contains far more water than most asteroids. It is small, yet it shows signs of geological processes that are usually associated with larger planets. And despite its quiet appearance, it may still harbor a hidden interior that continues to change even today. For scientists studying planetary formation, this makes Ceres incredibly valuable. It offers a glimpse into what the earliest building blocks of planets might have looked like billions of years ago, before Earth, Mars, and the other planets fully formed. Many bodies similar to Ceres may have existed throughout the solar system. Some of them eventually merged to form larger planets. Others were destroyed by collisions, but Ceres survived. It remains as one of the best preserved examples of a primitive protoplanet, a world that began to grow but never quite became a full-size planet. Its survival allows scientists to study processes that shaped the early solar system in remarkable detail. Every crater, mineral deposit, and geological structure on Ceres tells a story about the environment in which it formed. And the more researchers examine the data from the Dawn mission, the more it becomes clear that this small dwarf planet is far more complex than anyone once imagined. A quiet grey sphere drifting through the asteroid belt, yet beneath that calm surface lies a world shaped by water, chemistry, and time. A world that still holds many secrets waiting to be uncovered. At first glance, Ceres might appear quiet and unchanging, a grey crater dwarf planet drifting silently through the asteroid belt. But when scientists began studying its surface more carefully, they realized that the landscape of Ceres tells a much more complicated story. Every crater, ridge, and bright deposit is a record of events that unfolded over billions of years. To understand that story, researchers first looked at one of the most common features on the dwarf planet, impact craters. Like many worlds in the solar system, Ceres has been shaped by countless collisions with asteroids and other space debris. These impacts began shortly after the dwarf planet formed and continued throughout its long history. Each collision carved a crater into the surface, leaving behind scars that still remain today. Yet, something about these craters immediately puzzled scientists. On rocky worlds like the Moon or Mercury, craters tend to remain sharp and well preserved for billions of years. Their edges are steep, their shapes are clearly defined, and their interiors often contain central peaks formed by the rebound of the surface after an impact. But many craters on Ceres look different. Instead of sharp edges, some of them appear softened and rounded, as though the surface has slowly sagged or relaxed over time. Others are shallower than expected, almost as if the terrain beneath them gradually flowed and partially filled them in. This observation suggested that the crust of Ceres behaves very differently from solid rock. The most likely explanation is that the dwarf planet's surface contains a mixture of rock, ice, and salts. Over long periods of time, this material may slowly deform under its own weight, subtly reshaping the landscape. This slow movement is extremely gradual, far too slow to notice on human timescales, but over millions of years it can significantly alter the appearance of craters and mountains. The idea that Ceres has a partially icy crust helped explain another unusual discovery. When scientists counted the number of large craters across the surface, they noticed something strange. Ceres has fewer large impact basins than expected. Given its age, the dwarf planet should have been struck by enormous asteroids many times in the past. These impacts would normally create massive basins hundreds of kilometers wide, yet only a few such basins have been identified. One possible explanation is that these ancient basins once existed, but gradually relaxed and flattened over time as the icy crust slowly flowed. In other words, the surface of Ceres may have the ability to partially erase the deepest scars left by ancient impacts. Another intriguing feature discovered by the Dawn spacecraft is the presence of long fractures and ridges scattered across parts of the surface. These fractures look like cracks that formed when the crust was stretched or stressed. Some of them run for dozens of kilometers across the terrain. What could have caused such stress on a world as small as Ceres? Scientists believe the answer may lie beneath the surface. If the interior of Ceres once contained liquid water or briny reservoirs, changes in temperature could have caused the interior materials to expand or contract. These movements would place stress on the crust above, eventually causing it to crack. Some of these cracks may have acted as pathways for briny liquids rising from deeper layers. This process could explain how salts and other minerals reach the surface in places like Occator Crater. But the most dramatic geological feature discovered on Ceres is something that seems almost impossible for such a small world. Rising above the surrounding terrain is a mountain called Ahuna Mons. At first glance, Ahuna Mons looks almost like a giant pyramid standing alone on the surface. It rises about 4 kilometers high, making it one of the tallest features on the entire dwarf planet. What makes Ahuna Mons even more remarkable is its shape. Unlike mountains formed by tectonic activity on Earth, Ahuna Mons has smooth slopes and a structure that resembles volcanic domes seen on other worlds. But Ceres is far too small to have traditional volcanoes fueled by molten rock. Instead, scientists believe Ahuna Mons may be something much stranger, a cryovolcano. Cryovolcanoes are icy volcanoes that erupt not molten lava, but slushy mixtures of water, ice, and salt. These eruptions occur when subsurface materials become warm enough to move and are pushed upward through cracks in the crust. When the material reaches the surface, it quickly freezes, building up layers that eventually form large icy mountains. If Ahuna Mons is indeed a cryovolcano, it means that Ceres once had, or may still have, internal conditions capable of driving such activity. That possibility was once considered extremely unlikely for a body of this size, yet the evidence continues to grow. Another clue comes from the age of Ahuna Mons itself. The mountain appears surprisingly young compared to the surrounding terrain, while much of Ceres' surface shows signs of ancient impacts billions of years old. Ahuna Mons seems to have formed within the last few 100 million years. In geological terms, that is relatively recent. This suggests that Ceres remained active long after scientists once believed it had completely cooled. Even more fascinating is the possibility that cryovolcanic activity might not be entirely finished. Some studies of dawn data suggest that the bright deposits in Occator Crater could have formed within the last few million years, and perhaps even more recently. If true, this would mean that Ceres is not entirely dormant. Instead, it may still experience slow geological changes beneath its surface. Another remarkable discovery made by the Dawn mission involves the distribution of water ice across Ceres. Although much of the surface appears dark and rocky, scientists found evidence that water ice exists just below the surface in many regions. In fact, the dwarf planet's polar regions appear to contain permanently shadowed craters where sunlight never reaches the ground. Inside these frozen craters, temperatures are so cold that water ice could remain stable for billions of years. These areas may serve as natural ice traps, preserving ancient water that has been protected from sunlight since the earliest days of the solar system. This makes Ceres particularly interesting for scientists studying the origin and distribution of water across planetary bodies. Some researchers even believe that objects like Ceres may have played an important role in delivering water to the inner planets during the early history of the solar system. During that chaotic era, countless asteroids and dwarf planets collided with young worlds like Earth and Mars. If water-rich bodies similar to Ceres were among those impactors, they may have helped supply the ingredients necessary for oceans to form. Studying Ceres today may therefore provide clues about one of the biggest questions in planetary science: where did Earth's water come from? But Ceres may also tell us something even deeper about the evolution of small planetary bodies. For a long time, scientists believed that only large planets and moons could remain geologically active for billions of years. Smaller bodies were assumed to cool quickly and become completely inactive, yet discoveries on Ceres are challenging that assumption. Despite its modest size, the dwarf planet shows evidence of internal layering, possible briny reservoirs, cryovolcanic activity, and surface changes that occurred relatively recently. All of this suggests that even small worlds can remain surprisingly dynamic under the right conditions. The key ingredient may be salt. Salty water freezes at much lower temperatures than pure water. This means that briny liquids can remain fluid deep inside a cold world, long after ordinary water would have frozen solid. Inside Ceres, these salty reservoirs may act as slow-moving pockets of liquid trapped beneath layers of rock and ice. Over millions of years, pressure from these liquids could occasionally push them upward toward the surface, creating the geological features we see today. This slow internal activity may still be happening even now, quietly reshaping parts of the dwarf planet beneath its silent exterior. And that realization has transformed Ceres from what was once thought to be an unremarkable asteroid into something far more fascinating. A world where water once flowed, a world where salty brines may still move beneath the surface, and a world that continues to surprise scientists with every new piece of data we uncover. In the vast emptiness between Mars and Jupiter, Ceres remains a quiet but extraordinary reminder that even the smallest worlds can hold remarkable secrets, waiting patiently for us to discover them. For much of the 20th century, scientists believed they understood the basic structure of the asteroid belt. It was thought to be a region filled with countless rocky fragments, leftovers from the formation of the solar system, that never managed to assemble into a planet. Jupiter's enormous gravity played a major role in preventing that planet from forming. As the early solar system evolved, Jupiter's powerful gravitational influence constantly stirred up the surrounding material. Instead of merging together into a single large body, many of the smaller objects were scattered, broken apart, or sent into unstable orbits. The result was the asteroid belt we see today. Within this region, most objects remain small. Many are only a few kilometers wide, and even the largest asteroids are tiny compared to planets. But Ceres is different. Its size, shape, and composition suggest that it may once have been on the path toward becoming something much larger. In fact, some scientists describe Ceres as a frozen protoplanet. A protoplanet is an early planetary body that began forming during the chaotic early days of the solar system, but never finished the process of becoming a full planet. Billions of years ago, the asteroid belt may have contained several objects similar to Ceres, bodies that were gradually growing as they collided with smaller planetesimals around them. If the conditions had been slightly different, these objects might eventually have merged into a larger rocky planet. But Jupiter's gravity disrupted that process. The powerful gravitational disturbances from the giant planet caused many of these early protoplanets to collide violently or be ejected from the region entirely. Over time, the asteroid belt lost most of its original mass. Ceres survived, but instead of continuing to grow, it remained isolated, a lone dwarf planet surrounded by smaller asteroids. Because it stopped growing relatively early in the solar system's history, Ceres preserved many features that scientists believe resemble the building blocks of planets. Studying it is therefore like examining a fossil from the era when planets themselves were still forming. One of the most important clues to Ceres' early history lies in its chemical composition. Spectroscopic measurements taken by spacecraft and telescopes reveal that the surface of Ceres contains large amounts of hydrated minerals. These minerals form when rock chemically reacts with liquid water. On Earth, similar processes occur when groundwater slowly alters the composition of rocks underground. Finding hydrated minerals across much of the surface strongly suggests that water once circulated extensively within the interior of Ceres. But the evidence goes even further. Scientists have also detected ammonia-bearing compounds in certain regions of the dwarf planet's crust. Ammonia is particularly interesting because it is far more common in the colder outer regions of the solar system, where temperatures are low enough for it to remain stable. This raises an intriguing possibility. Ceres may not have formed exactly where it is today. Instead, it might have originated farther away from the Sun, perhaps beyond the orbit of Jupiter, before migrating inward to its current position in the asteroid belt. Planetary migration is now known to have played a major role in shaping the solar system. During its early evolution, the giant planets likely moved through the disk of material surrounding the young sun. These movements could have scattered icy bodies inward while pushing other objects outward. If Ceres formed in a colder region rich in ice and ammonia, it would explain why the dwarf planet contains such a high percentage of water compared to most asteroids. This idea would also mean that Ceres represents a mixture of inner and outer solar system materials, a rare combination that could provide valuable clues about how the early solar system evolved. Another fascinating aspect of Ceres is the presence of clay minerals, also known as phyllosilicates. These minerals form when water interacts with silicate rock over long periods of time. On Earth, they are commonly found in ancient ocean sediments and weathered rocks. Their presence on Ceres indicates that water-rock interactions likely occurred deep within the dwarf planet for millions or even billions of years. This slow chemical transformation could have gradually altered much of the interior, creating a mixture of hydrated minerals, salts, and ice. Over time, this mixture may have produced the briny liquids that later reached the surface through fractures and impacts. In other words, Ceres may have experienced a form of subsurface hydrothermal activity, albeit on a smaller scale than what occurs on larger planets or moons. Hydrothermal systems are especially interesting to scientists because they can create environments where complex chemistry takes place. On Earth, hydrothermal vents on the ocean floor support rich ecosystems of life. Despite the absence of sunlight, these environments are powered by chemical energy rather than photosynthesis. While there is currently no evidence that life ever existed on Ceres, the presence of water, salts, organic molecules, and internal heat suggests that its interior may once have had the ingredients necessary for complex chemical reactions. In addition to its chemical composition, the temperature conditions on Ceres also play an important role in shaping its evolution. Because it lies relatively far from the Sun, the dwarf planet receives much less solar energy than Earth or Mars. Surface temperatures typically range between -40 and -105 degrees Celsius, depending on the time of day and location. These extremely cold temperatures help preserve water ice beneath the surface. However, sunlight can still cause ice exposed on the surface to slowly sublimate, turning directly into vapor and escaping into space over long periods of time. This process may gradually remove ice from exposed areas while leaving behind darker, dust-covered regions. This could explain why most of the visible surface appears dry and rocky, even though large amounts of ice may exist just below the crust. In fact, radar and neutron measurements from the Dawn spacecraft indicate that ice-rich material may lie only a few meters beneath the surface in many regions. This means that Ceres may contain a hidden layer of frozen water extending across much of the dwarf planet. One particularly interesting region lies near the poles. Some craters near the North Pole are permanently shadowed, meaning that sunlight never reaches their floors. These locations remain extremely cold, potentially allowing water ice to remain stable for billions of years. These permanently shadowed craters could serve as natural repositories of ancient ice, preserving material that has remained unchanged since the earliest history of the solar system. Such regions are of great interest for future exploration missions. If a spacecraft were ever sent to land on Ceres, these icy deposits could provide valuable samples that reveal information about the dwarf planet's past. Even more intriguingly, these frozen reservoirs might contain chemical records of the early solar system, perhaps even organic compounds that formed before Earth itself existed. For planetary scientists, Ceres represents a remarkable opportunity. It is close enough to Earth to be studied with spacecraft, yet primitive enough to preserve clues about the earliest stages of planetary evolution. Every crater, mineral deposit, and geological structure on the dwarf planet serves as a piece of a much larger puzzle. A puzzle that may eventually reveal how the building blocks of planets formed, evolved, and spread throughout the solar system. And perhaps most importantly, it reminds us that even small worlds that once seemed insignificant, can hold extraordinary stories about the origins of everything we see today. Ceres, quietly orbiting between Mars and Jupiter, is not just another asteroid. It is a window into the deep past of our cosmic neighborhood. When the Dawn spacecraft finally settled into orbit around Ceres in 2015, scientists began one of the most detailed investigations ever conducted on a dwarf planet. For decades, researchers had been able to observe Ceres only as a distant blur through telescopes. Now, for the first time, humanity had a spacecraft circling this mysterious world, sending back thousands of images and measurements. What Dawn revealed was both familiar and surprising. At first glance, the surface of Ceres appeared gray, dusty, and heavily cratered, very similar to many other small bodies in the solar system. The terrain was dominated by ancient impact scars, some stretching for dozens of kilometers across the landscape. But as the spacecraft continued mapping the surface in greater detail, scientists began noticing patterns that hinted at something more complex. The distribution of craters, for example, was uneven. Some regions were densely covered in impacts, suggesting they had remained unchanged for billions of years. Other areas appeared smoother and less cratered, indicating that they might have been resurfaced by geological processes more recently. This observation suggested that the surface of Ceres had not remained static throughout its history. Instead, parts of it had been reshaped by processes occurring beneath the crust. One of the most striking examples of this resurfacing is found inside Occator Crater, the same crater where the mysterious bright spots were discovered. Occator itself is about 90 kilometers wide and roughly 4 kilometers deep, making it one of the largest impact features on Ceres. But what truly sets it apart is the complex structure inside the crater. At its center lies a bright deposit known as Ceres facula, surrounded by smaller bright patches scattered across the crater floor. These bright areas are not just visually striking, they are also geologically significant. Detailed measurements revealed that the deposits are composed primarily of sodium carbonate, a type of salt that forms when salty water evaporates. The presence of this mineral suggests that liquid brines once reached the surface in this location. But how did those brines get there? The most likely explanation involves the violent impact that created the crater itself. When the asteroid struck Ceres billions of years ago, the collision would have fractured the crust deeply. These fractures may have allowed briny liquids from beneath the surface to slowly rise upward. Over time, these brines could have seeped onto the crater floor through small vents or cracks. Once exposed to the vacuum of space, the liquid would rapidly evaporate, leaving behind bright salt deposits. But the story may not end there. Recent studies suggest that this process might have continued for millions of years after the original impact. In fact, some of the salt deposits in Occator appear to be geologically young, possibly only a few million years old. In planetary terms, that is almost yesterday. This raises the remarkable possibility that Ceres experienced very recent geological activity, long after scientists once believed the dwarf planet had completely cooled. Evidence supporting this idea comes from subtle changes in the structure of the deposits themselves. The central dome inside Occator Crater appears to have formed from material pushed upward from below the surface. This dome, known as Cerelia Tholus, may have formed when pressurized briny fluids forced their way upward and then froze once they reached the surface. If this interpretation is correct, it means that Ceres may have remained internally active far longer than expected for a body of its size. Another intriguing discovery made by the Dawn spacecraft was the presence of haze-like clouds above parts of Occator Crater. In certain images taken when the sun was low on the horizon, scientists noticed faint bright patches that appeared to hover above the crater floor. These features were initially controversial. Some researchers suggested that the haze might be caused by water vapor or fine particles escaping from the surface, possibly as the briny deposits slowly released gas. Others argued that the effect might simply be an optical illusion created by sunlight reflecting off the bright salt deposits. Even today, the exact explanation remains uncertain, but if gas is occasionally escaping from the surface, it would provide further evidence that the interior of Ceres still contains reservoirs of volatile materials. Another region that fascinated scientists is the large mountain Ahuna Mons, which we discussed earlier. From orbit, Ahuna Mons appears almost isolated from the surrounding terrain. Its steep slopes and smooth surface make it look very different from the surrounding cratered plains. High-resolution images revealed streaks of bright material running down the sides of the mountain. These streaks may represent icy flows or frozen cryovolcanic material that once erupted from beneath the surface. If Ahuna Mons is indeed a cryovolcano, it would suggest that Ceres once had, or perhaps still has, pockets of slushy material capable of rising through the crust. This type of activity is more commonly associated with icy moons such as Enceladus or Europa, making its presence on Ceres particularly surprising. Beyond these dramatic geological features, the Dawn mission also mapped the chemical composition of the surface in extraordinary detail. Spectrometers aboard the spacecraft analyzed sunlight reflected from the dwarf planet, allowing scientists to identify specific minerals present on the surface. The results confirmed the presence of large amounts of hydrated minerals, salts, and carbon-rich compounds. These materials indicate that water once played a major role in shaping the interior of Ceres. They also suggest that the dwarf planet experienced complex chemical reactions between water and rock, processes that may have occurred for millions of years beneath the surface. Another fascinating discovery came from measurements of hydrogen concentrations across the surface. These measurements revealed that certain regions contain unusually high amounts of hydrogen, which is often associated with the presence of water or hydroxyl molecules. The highest concentrations were found near the polar regions, where temperatures are extremely low. In these cold environments, water ice may remain stable just beneath the surface for extremely long periods of time. Some craters near the North Pole are permanently shadowed, meaning that sunlight never reaches their interiors. Inside these frozen traps, water ice could survive for billions of years without sublimating. Such regions are considered potential targets for future exploration missions because they may preserve pristine ice dating back to the early solar system. In many ways, Ceres now appears to be something like a hybrid world. It shares characteristics with rocky asteroids, icy moons, and even small planets. Its interior may contain layers of rock mixed with ice and salts. Its surface displays evidence of impacts, geological relaxation, cryovolcanic activity, and chemical alteration by water. And its history stretches back to the earliest days of planetary formation. Perhaps most fascinating of all is the possibility that Ceres may still be slowly evolving even today. Unlike large planets which experience dramatic geological processes like earthquakes and volcanoes, the changes on Ceres likely occur at an incredibly slow pace. Briny liquids may move gradually through the interior over millions of years. Ice within the crust may slowly shift and deform, and occasional impacts may fracture the surface, allowing buried materials to reach the light of the sun. These quiet processes continue to shape the dwarf planet long after its formation. For scientists studying planetary evolution, Ceres offers a rare opportunity. It is close enough to study with spacecraft, yet primitive enough to preserve clues about the earliest history of the solar system. Every new measurement from the Dawn mission has helped reveal another piece of the puzzle. A puzzle that tells the story of a small world that turned out to be far more dynamic than anyone once imagined. And despite everything we have learned, many questions remain unanswered. How much liquid still exists beneath the surface? Could future missions detect ongoing activity more clearly? And what other secrets might be hidden beneath the quiet grey plains of this distant dwarf planet? Ceres may be small, but it continues to challenge our understanding of how worlds form, evolve, and change over time. For much of modern astronomy, the dwarf planet Ceres was considered a quiet relic of the solar system's earliest days, a frozen survivor drifting through the asteroid belt. But the discoveries made by the Dawn spacecraft began to challenge that assumption in ways few scientists expected. Instead of being a simple rock in space, Ceres revealed itself as a world with an unusually complex internal history. Beneath its dusty grey surface lies evidence of water, salts, and geological processes that have shaped the dwarf planet over billions of years. To understand how unusual this is, it helps to compare Ceres with other bodies of similar size. Most asteroids are nothing like planets. They are irregular chunks of rock that never developed enough gravity to shape themselves into spheres. Their interiors are often loose collections of rubble held together weakly by gravity. Ceres is very different. Its spherical shape indicates that at some point in its history, the materials inside the dwarf planet were able to move and settle under gravity. This process requires heat, enough heat to soften or partially melt internal materials. But where could that heat have come from? In the earliest days of the solar system, young planetary bodies contained radioactive elements that generated heat as they decayed. In larger objects, this heat could melt ice and even allow rock to slowly flow. For Ceres, this early heating may have triggered the formation of an internal ocean layer. Deep beneath the crust, water mixed with dissolved salts could have formed a global layer of liquid surrounding the interior. This ocean would not have been like Earth's oceans. It would have existed beneath a thick outer shell of rock and ice, hidden from space by kilometers of crust. Over time, however, the interior of Ceres gradually cooled. As heat escaped into space, the liquid ocean likely began to freeze. Ice would slowly form, thickening the outer shell and trapping remaining pockets of salty liquid within the interior. These trapped reservoirs of briny water may still exist today. Because salt lowers the freezing point of water, these brines could remain liquid at temperatures where pure water would freeze solid. Scientists now believe that these salty reservoirs may play an important role in shaping the geological features observed on Ceres. Occasionally, internal stresses caused by impacts, temperature changes, or pressure from below may create fractures in the crust. When these fractures reach deep enough, they could allow briny liquids to slowly seep upward toward the surface. Once exposed to the vacuum of space, the liquid would quickly evaporate or freeze, leaving behind bright mineral deposits like those found in Occator Crater. But Ceres may hold more surprises than just briny reservoirs. Another remarkable discovery made by the Dawn mission involved organic molecules detected on the surface. Organic molecules are carbon-based compounds that are often associated with biological processes. However, they can also form through non-biological chemistry in space. On Ceres, these organic materials were discovered near a region called Occator Crater. The concentrations detected there were unusually high compared to typical background levels found on asteroids. This discovery raised an important question. Did these organic compounds originate inside Ceres, or were they delivered by impacts from carbon-rich asteroids or comets? Both possibilities are fascinating. If the organics formed within Ceres itself, it would suggest that chemical reactions involving water, minerals, and heat may have occurred deep within the dwarf planet's interior. Such reactions could create complex molecules over long periods of time. On the other hand, if the organics were delivered by impacts, it would demonstrate how materials essential for complex chemistry can spread throughout the solar system. In either case, the presence of organic compounds adds another layer to the story of Ceres. It shows that this dwarf planet contains not only water and salts, but also carbon-based materials that may have played a role in the early chemistry of planetary bodies. Another intriguing aspect of Ceres is its relationship with other water-rich worlds in the solar system. Many moons orbiting the giant planets are known to contain large amounts of water ice. Some, such as Europa and Enceladus, even possess hidden oceans beneath their icy surfaces. These moons are located far from the sun, where temperatures are cold enough for ice to remain stable. Ceres, however, lies much closer to the sun than these icy moons. Its location between Mars and Jupiter places it in a region where water ice is less stable over long periods. Yet, despite this, Ceres appears to contain large quantities of water. This suggests that the dwarf planet may have formed under very different conditions than the rocky planets nearby. Some researchers believe that Ceres may have originally formed farther out in the solar system, in a colder region where ice was abundant. Later, gravitational interactions with the giant planets could have moved it inward to its present orbit. If that idea is correct, Ceres may represent a rare bridge between the inner and outer solar system. It may contain materials from both regions, rocky minerals typical of inner planets, and icy compounds more common in the outer solar system. Studying such a body could provide valuable clues about how materials were distributed during the formation of the solar system. Another important discovery made by the Dawn mission involves the age of different regions on the surface. By counting the number of craters in various areas, scientists can estimate how long those surfaces have remained unchanged. Regions with many craters are usually very old, while smoother areas with fewer craters may have been resurfaced more recently. On Ceres, the crater record shows a surprising variety. Some areas appear extremely ancient, dating back more than 4 billion years. Other regions seem significantly younger, suggesting that geological activity reshaped them long after the dwarf planet formed. This pattern supports the idea that internal processes, such as the movement of briny liquids or cryovolcanic eruptions, may have altered parts of the surface relatively recently. For a body of Ceres size, this is remarkable. Most small planetary bodies cool quickly and become completely inactive after their formation, Yet Ceres seems to have remained active for far longer than scientists once believed possible. Even today, the dwarf planet may still be slowly evolving beneath its quiet exterior. Pressure from trapped briny liquids could continue to reshape the crust. Impacts from asteroids may fracture the surface and expose buried ice, and chemical reactions within the interior may gradually alter the composition of the crust. All of these processes occur incredibly slowly, unfolding over millions of years rather than days or centuries. But they remind us that Ceres is not just a frozen relic, it is a world that has experienced a long and complex history, one shaped by water, chemistry, impacts, and time. Perhaps most fascinating of all is the role Ceres may play in helping scientists understand the early solar system. Because it formed very early in planetary history and avoided major collisions that might have destroyed it, Ceres may preserve ancient materials that date back to the era when the planets themselves were still forming. Studying these materials could help answer some of the biggest questions in planetary science. How did water spread throughout the solar system? How common are subsurface oceans on small worlds? And what kinds of environments existed on early planetary bodies billions of years ago? Ceres may hold important clues to these mysteries. A small dwarf planet, drifting quietly through the asteroid belt. Yet beneath its ancient surface lies a story that stretches back to the very beginning of the solar system. A story that scientists are still only beginning to understand. When scientists first began to understand the strange features of Ceres, one realization slowly became clear. This small dwarf planet might represent a completely different category of world than researchers had previously imagined. For centuries, astronomy divided objects in the solar system into simple groups: planets, moons, asteroids, and comets. Each category seemed well understood. Planets were large and geologically active. Asteroids were small and inert. Moons often reflected the characteristics of the planets they orbited. But Ceres does not fit comfortably into any of these categories. It is too large and complex to be considered a typical asteroid, yet far too small to behave like a full-sized planet. It possesses characteristics of icy moons, but it orbits the sun independently rather than circling a giant planet. Because of this, scientists now see Ceres as something of a transitional world, a body that lies somewhere between asteroid and planet. This realization is important because it changes how we think about the formation of planetary systems. In the early solar system, the line between asteroid and planet may not have been as clear as we once believed. Instead, there may have been many intermediate bodies, similar to Ceres, objects that had begun developing complex internal structures but never completed the process of becoming full planets. These bodies are sometimes referred to as protoplanets, early planetary embryos that formed during the chaotic period when the solar system was still assembling itself. Many of these protoplanets likely collided with each other, merging to form larger worlds like Earth and Mars. Others may have been destroyed by violent impacts or thrown out of the solar system entirely. Ceres is unusual because it survived, protected by chance and location. It remained largely intact, while the rest of the asteroid belt lost much of its mass. As a result, Ceres preserves a record of processes that occurred during the earlier stages of planetary formation. One of the most fascinating aspects of this record is the presence of water-related minerals across much of the dwarf planet's surface. Hydrated minerals, minerals that formed in the presence of water, appear almost everywhere scientists have looked on Ceres. These minerals suggest that water once interacted extensively with rock inside the dwarf planet. But water alone does not explain the complexity of Ceres' chemistry. Spectroscopic measurements have also revealed the presence of carbon-bearing materials, including compounds that resemble organic molecules. These materials may have formed through chemical reactions involving water, carbon dioxide, and minerals within the interior of the dwarf planet. Such reactions can occur when water circulates through porous rock, slowly dissolving and redepositing minerals over time. On Earth, similar chemical processes occur deep underground, where groundwater interacts with hot rock to produce complex mineral deposits. If something similar happened on Ceres, it would suggest that the interior of the dwarf planet once hosted a surprisingly dynamic chemical environment. Of course, Ceres is extremely cold today. Surface temperatures rarely rise above -40 degrees Celsius, and in many areas, they are far colder. Under such conditions, liquid water cannot survive on the surface for long. Any exposed water quickly turns to vapor and escapes into space. But beneath the surface, conditions may have been very different in the past. Scientists believe that early in its history, Ceres may have contained a large internal ocean made of salty water. This ocean would have been trapped beneath a crust of rock and ice, protected from the vacuum of space. Over time, as the dwarf planet cooled, this ocean likely began to freeze. Yet, because the water contained dissolved salts and other chemicals, it may not have frozen completely. Instead, pockets of briny liquid may have remained trapped beneath the crust, slowly circulating through fractures and porous layers of rock. These brines may still exist today. In fact, some scientists believe that the bright salt deposits inside Occator Crater are the result of these subsurface liquids slowly reaching the surface and evaporating. If this interpretation is correct, Ceres may still be geologically active, albeit in a very slow and subtle way. Rather than violent eruptions or earthquakes, the activity on Ceres likely involves gradual movement of salty liquids beneath the crust over millions of years. This kind of slow geological evolution is difficult to detect, but the evidence from the Dawn mission suggests that it may still be occurring. Another remarkable aspect of Ceres is its surface gravity, which is extremely weak compared to Earth. Standing on the surface of Ceres would feel very different from standing on our planet. Gravity there is only about 3% as strong as Earth's gravity. An astronaut weighing 70 kilograms on Earth would weigh barely 2 kilograms on Ceres. Under such low gravity, even small movements could send a person drifting upward in long, slow arcs. Dust and debris from impacts would behave differently as well. When asteroids strike the surface, the material they eject can travel long distances before settling again. This may explain why some craters on Ceres appear surrounded by smooth plains of redistributed debris. Over time, repeated impacts may have gradually mixed the surface materials, creating the dusty crust we see today. Another factor shaping the landscape is the absence of an atmosphere. Ceres has no thick layer of air like Earth does. Without an atmosphere, there is no wind, no rain, and no weather to erode the surface. This means that geological features can remain visible for extremely long periods of time. Craters formed billions of years ago may still be recognizable today, unless they have been altered by internal processes such as ice movement or cryovolcanism. The lack of an atmosphere also means that the sky above Ceres would look dramatically different from the sky on Earth. During the day, the sun would appear slightly smaller and dimmer than it does from our planet. The sky itself would remain completely black even when the sun is shining. Stars would remain visible throughout the day, scattered across the darkness of space. From the surface, the surrounding landscape would appear quiet and still, a frozen world illuminated by distant sunlight. But appearances can be deceiving. Beneath the calm exterior, Ceres holds evidence of ancient activity and chemical processes that once shaped its interior. Another intriguing discovery, made by the Dawn mission, involves the distribution of water ice near the poles. In some polar craters, sunlight never reaches the crater floor. These regions remain in permanent shadow, creating extremely cold environments. Temperatures in these shadowed areas may be cold enough for water ice to remain stable for billions of years. Scientists believe that these craters could act as natural cold traps, preserving ice that may have accumulated over long periods of time. If future missions were able to explore these regions directly, they might uncover pristine samples of ancient ice, material that has remained unchanged since the early solar system. Such samples could provide valuable insights into the distribution of water and organic compounds during the formation of planets. This possibility has led some researchers to consider whether Ceres might one day become a target for future exploration missions, perhaps even robotic landers or sample return spacecraft. Although no such mission has yet been approved, interest in Ceres continues to grow. Its unique combination of water, salts, organic compounds, and geological features makes it one of the most scientifically intriguing worlds in the inner solar system. What once seemed like an ordinary asteroid has revealed itself to be something far more interesting. A small, distant world shaped by water and chemistry. A world that may still hold hidden reservoirs beneath its crust, and a world that preserves clues about the earliest chapters of our solar system's history. As scientists continue to analyze the data returned by the Dawn spacecraft, each new discovery brings us closer to understanding the true nature of this mysterious dwarf planet. Ceres may be small, but it has proven to be one of the most fascinating worlds ever explored. For centuries, astronomers thought they understood the general structure of the solar system. The inner region was dominated by rocky planets like Mercury, Venus, Earth, and Mars. Beyond them lay the asteroid belt, a region of scattered debris that never formed into a planet. Farther still were the giant worlds of Jupiter and Saturn, followed by the icy outer planets and the distant Kuiper belt. In this picture, the asteroid belt seemed relatively simple. It was viewed as a collection of small, primitive rocks orbiting quietly between Mars and Jupiter, leftovers from the solar system's formation that never managed to grow into anything larger. But Ceres has gradually changed that perspective. As scientists studied this dwarf planet more closely, it became clear that the asteroid belt may not be as simple as once believed. Instead of containing only inert rocky fragments, the belt may host objects with surprisingly complex histories. Ceres is the best example of this. It is not merely the largest asteroid belt object. It is a world that shows signs of water, internal chemistry, and geological activity. These characteristics place it closer to icy moons or small planets than to ordinary asteroids. This realization has led researchers to reconsider how planetary systems form. During the early stages of the solar system, countless objects similar to Ceres likely existed. Some were larger, some smaller, but many were undergoing similar processes: internal heating, chemical reactions, and structural differentiation. In other words, the early solar system may have been filled with planetary embryos, worlds that were still evolving and changing before the final planets emerged. Most of those early bodies did not survive. Some collided and merged to form larger planets. Others were shattered by impacts or scattered by the gravitational influence of the giant planets. Many were likely ejected into interstellar space. Ceres endured because it remained in a relatively stable orbit within the asteroid belt. It preserved a record of processes that occurred during the earliest chapters of solar system history. One of the most fascinating aspects of this record is the role water appears to have played. Water is one of the most important substances in planetary science. It influences geological activity, chemical reactions, and the potential habitability of environments across the solar system. For a long time, scientists assumed that water-rich worlds were primarily located far from the sun, where temperatures were low enough for ice to remain stable. But Ceres challenges that assumption. Despite orbiting much closer to the sun than icy moons like Europa or Enceladus, Ceres contains significant quantities of water. Much of it is locked in the form of ice or hydrated minerals within the crust. This discovery suggests that water may have been far more widespread in the inner solar system than previously thought. Some researchers even believe that objects similar to Ceres may have played a role in delivering water to Earth during its early formation. Billions of years ago, the young Earth was bombarded by countless asteroids and planetesimals. If some of those bodies contained water-rich materials, They could have contributed to the formation of Earth's oceans. Understanding the composition of Ceres, therefore, helps scientists explore one of the most fundamental questions in planetary science. How did water reach the inner planets? Another intriguing aspect of Ceres is the possibility that it once contained conditions suitable for complex chemical reactions. Inside the dwarf planet, water may have interacted with rock for millions of years, producing hydrated minerals and salts. These reactions can also generate chemical energy, the same type of energy that supports certain microbial ecosystems on Earth. On our planet, some microorganisms live deep underground, where sunlight never reaches them. Instead of relying on photosynthesis, they obtain energy from chemical reactions involving water and minerals. These environments demonstrate that life does not always require sunlight. Although there is currently no evidence that life ever existed on Ceres, the presence of water, organic molecules, and mineral interactions suggests that the dwarf planet may once have had environments capable of supporting complex chemistry. For scientists searching for habitable environments beyond Earth, this is an important realization. Habitability may not be limited to large planets with thick atmospheres. It may also exist in hidden environments beneath the surfaces of smaller worlds. Ceres could represent one of many such environments scattered throughout the solar system. Another key aspect of Ceres' story involves its long-term stability. Unlike many small bodies that experience violent changes early in their histories, Ceres appears to have evolved gradually over billions of years. Its interior cooled slowly, allowing chemical processes to occur over extended periods of time. The crust may have thickened as ice froze, while salty liquids remained trapped beneath the surface. Occasionally, fractures or impacts may have allowed these briny fluids to escape, forming the bright mineral deposits observed today. These slow processes highlight the unique nature of Ceres. It is neither a rapidly evolving volcanic world like Earth, nor a completely inert asteroid. Instead, it represents a middle ground where geological activity occurs on extremely long timescales. Millions of years may pass between significant events, yet those events leave clear traces that scientists can study today. The bright deposits in Occator Crater are one example. Another is the cryovolcanic mountain Ahuna Mons, which appears to have formed relatively recently in geological terms. Even the subtle relaxation of craters across the surface suggests that the crust continues to slowly adjust under the influence of gravity and internal processes. Taken together, these features paint a picture of a world that remains quietly active beneath its frozen exterior. Ceres may not erupt dramatically or shift rapidly like larger planets, but its interior still appears capable of subtle change. This realization has inspired growing interest in future missions to the dwarf planet. The Dawn spacecraft provided an extraordinary amount of information, but it was limited to remote observations from orbit. Scientists now wonder what might be discovered if a spacecraft were able to land on Ceres and directly analyze its surface materials. A lander could examine the composition of the bright salt deposits up close. It could drill into the crust to search for buried ice, and it might even detect traces of gases or other materials slowly escaping from beneath the surface. Such a mission could answer many of the questions that remain unresolved. Does liquid brine still exist beneath the crust? How deep are the layers of ice inside the dwarf planet? What processes created the organic molecules detected on the surface? And perhaps most intriguingly, what other surprises might be hidden within this small but complex world? For now, Ceres continues its quiet journey around the Sun, completing one orbit every 4.6 Earth years. From a distance, it appears calm and unremarkable, just another grey sphere drifting through the asteroid belt. But thanks to the discoveries made by the Dawn mission, we now know that beneath that quiet exterior lies a world shaped by water, chemistry, and ancient geological activity, a world that preserves clues about the earliest stages of planetary formation, and a world that reminds us that even the smallest bodies in our solar system can hold extraordinary stories waiting to be uncovered. For thousands of years, Humanity looked up at the night sky and imagined that the planets were the only true worlds in our solar system. Everything else, the countless small objects drifting between them, seemed insignificant. Asteroids were considered nothing more than fragments, debris left behind after the formation of the planets. Ceres changed that perception. What once appeared to be just another asteroid has gradually revealed itself as something far more complex, a world shaped by water, chemistry, and geological processes that unfolded over billions of years. It may be small compared to the planets, but its story is vast. When Ceres was first discovered in 1801 by the Italian astronomer Giuseppe Piazzi, it immediately sparked excitement among scientists. At the time, astronomers had been searching for a missing planet predicted to orbit between Mars and Jupiter. When Piazzi spotted a faint moving object in that region of the sky, many believed the long-awaited planet had finally been found. For a brief moment in history, Ceres was considered the fifth planet of the solar system. But as telescopes improved, more objects were discovered in the same region: Vesta, Pallas, Hygeia, and many others. It soon became clear that this area was not home to a single planet, but rather a vast population of smaller bodies. Ceres was eventually reclassified as an asteroid. Then in 2006, the International Astronomical Union introduced a new category for objects that were large enough to become spherical, but too small to dominate their orbital regions. These objects became known as dwarf planets. Ceres was placed in this category alongside Pluto, Eris, Haumea, and Makemake. But unlike the other dwarf planets, which reside far beyond Neptune in the Kuiper belt, Ceres occupies a unique position within the asteroid belt itself. This location makes it the only dwarf planet in the inner solar system. For scientists, that makes Ceres incredibly valuable. It is close enough to Earth that spacecraft can reach it without the enormous travel times required to explore the outer solar system. Yet, it preserves many features of primitive planetary bodies that formed billions of years ago. In other words, Ceres is both accessible and ancient, a rare combination that allows scientists to study the early solar system in remarkable detail. The Dawn mission provided the first real glimpse of this distant world. Over the course of its orbital survey, the spacecraft mapped nearly the entire surface, measured the composition of the crust, and revealed the internal structure of the dwarf planet. What it found surprised researchers again and again. Instead of a simple rocky asteroid, Ceres turned out to be a water-rich world with a layered interior. Its crust appears to be composed of a mixture of rock, ice, salts, and clay-like minerals. Beneath this crust may lie pockets of briny liquid, remnants of an ancient subsurface ocean that once existed early in the dwarf planet's history. Evidence of this ocean may still be visible today in the bright salt deposits scattered across the surface. Occator Crater, with its dazzling white mineral patches, has become one of the most iconic locations on Ceres. These deposits are thought to have formed when salty water from beneath the crust reached the surface and evaporated, leaving behind reflective minerals. The presence of these salts suggests that liquid brines may have remained trapped beneath the surface for millions of years after the crater formed. If so, Ceres may have experienced geological activity far more recently than scientists once believed possible. Another fascinating feature is the cryovolcanic mountain Ahuna Mons. Rising several kilometers above the surrounding plains, Ahuna Mons may have formed when slushy mixtures of ice, water, and salts erupted from beneath the surface and froze upon contact with the cold vacuum of space. Such cryovolcanic activity is usually associated with icy moons orbiting giant planets, not with small bodies in the asteroid belt. Yet here it appears on Ceres, suggesting that the dwarf planet's interior once possessed enough heat to drive these unusual eruptions. The discovery of organic molecules on the surface adds yet another layer to the story. Organic compounds are the building blocks of complex chemistry, and their presence on Ceres indicates that the dwarf planet contains materials rich in carbon. Whether these molecules formed within Ceres itself or arrived via impacts from other objects remains uncertain. Either way, their presence shows that Ceres contains ingredients that may have been important in the early chemical evolution of the solar system. Taken together, these discoveries reveal a world far more dynamic than anyone once imagined. A world where water once flowed beneath the surface. A world where salty liquids may still move slowly through hidden reservoirs. A world where geological processes, though subtle and slow, continue to shape the landscape. But perhaps the most important lesson from Ceres is what it teaches us about the nature of planetary formation. The solar system did not begin as a neat arrangement of fully formed planets. Instead, it began as a chaotic environment filled with countless planetary embryos, bodies like Ceres that were slowly growing and evolving. Some of these embryos collided and merged to form the planets we know today. Others were destroyed or scattered. Ceres survived because it avoided catastrophic collisions and remained relatively undisturbed for billions of years. It preserves a snapshot of the early solar system. By studying it, scientists gain insight into the processes that shaped the planets themselves. We learn how water interacted with rock in early planetary interiors. We learn how salts and minerals formed in subsurface oceans, and we learn how even small worlds can remain active far longer than once believed. Ceres reminds us that the solar system is full of unexpected complexity. Worlds that once seemed insignificant may hold important clues about our cosmic origins, and as technology advances, future missions may return to this dwarf planet to explore it in even greater detail. A lander might one day touch down on the surface, sampling the bright salt deposits inside Occator Crater. A drilling probe might search for buried ice beneath the crust. Perhaps one day a mission could even detect the faint traces of briny liquids still hidden within the interior. Until then, Ceres continues its quiet orbit around the Sun, completing a single revolution every 4.5 years. From a distance, it appears calm and silent, just another grey sphere drifting through the asteroid belt. But beneath that calm exterior lies a history billions of years old. A history written in water, minerals, impacts, and time. A history that reminds us that even the smallest worlds can hold extraordinary secrets. And in the vast darkness between Mars and Jupiter, Ceres stands as a reminder that the solar system still has many mysteries waiting to be explored.